Hello guys, welcome to another video in the series of coding. Today we are going to do a problem. It's called implementing Dijkstra's algorithm. Let's try to understand what is this algorithm. So what is Dijkstra's algorithm? It's a very famous algorithm. Let's see what is it and when is it used and when can it fail. Okay, so what it is just used to find minimum distance, right? In a graph, suppose a weighted graph is given and you want to find minimum distance from a given source node to, let's say, all other nodes. Okay, from a source node to all other nodes. If you want to find the minimum distance in a graph, you can use the Dijkstra's algorithm. Okay. Now, when can it be used? Can it be used for all types of graphs? Let's see. So first of all, if you have to find minimum distance, obviously it's a weighted graph, right? Okay. Next, when can it be used? It can be used for both cyclic as well as acyclic graphs. Okay. So this, whether the graph is cyclic or it is acyclic, it doesn't matter. It can be used for both type of graphs. Okay. And what about directed or undirected? Whether it is a directed graph or it is a non-directed graph, Dijkstra's algorithm can be used. Okay. It can be used in all the three cases. Now, when can it not be used? Okay. When will it fail? So Dijkstra's algorithm will not work when you have negative weights. Okay. If you have negative weights, it will not work. It works only for positive weights. So the weights in the graph should be positive, then it can be used to find the minimum distance between a source node to all other nodes. Okay. Now let's see what is Dijkstra's algorithm. So first we will see a working of Dijkstra's algorithm and then we'll code it. So let's see. Let's say I have given you a source node. I am calling that source node 0. Okay. I want you to give me the distance of all the other nodes, right? Of all the other nodes, which are nodes 1, node 3, node 2. Okay. From source node, which is 0. I want you to give me the distance. But the distance should be minimum, right? Distance should be minimum from the source node to all other nodes. Okay. How do we do this? Okay. So let's start. So in the Dijkstra's algorithm, the first thing that we can do is we can just do one simple thing. Mark the source node as 0, right? Mark the distance of the source node as 0 because we are starting from the source node. Then what will you mark? All other distances. You mark all other distances as infinity. Okay. So this is the working. So source node will be marked as 0. All other distances will be marked as infinity. Okay. Now we have done this. Now what is the next step that we want to do? Okay. We can also keep track of a visited array. You can also declare a visited array and you can see which nodes you are visiting, which nodes you have not yet covered. Okay, so that is what you can do. So let's say that you are visiting node number 0 first, so that will be a part of your visited array. Okay, and whether you have visited or not, you can mark all the nodes as false initially. So initially we will mark all the nodes as false, and when we visit a node we will make it true. Okay, and then the next thing, which is the most important thing, you will create a distance array. Why? Because this is what you want to find, right? You want to find the distance of the of all other nodes from the source node. So what will be the distance of source node from source node? It will be 0, right? Source node is at a distance of 0 from itself. What about all other nodes? They are at distance of infinity. Okay, so this is the basic initialization, just simple steps. You can mark a distance array, you can mark a visited array, and you can mark the source node as 0 because it is at a distance of 0 from itself, and all other nodes as infinity. Okay, now let's start with the algorithm. So what we'll do, this is the first node that we are visiting, right? This is the first node. 0 is the first node that we are visiting. So we will mark it as true. Okay, we will mark it as true, and its distance is already 0. Okay, now we will visit its neighbors. So we will visit the neighbors of 0. Okay, so when we are visiting each neighbor, let's visit each neighbor one by one. First, let's visit. Suppose we are visiting. Uh, we can choose any neighbor, right? So if we are going by the order, let's say we are visiting the neighbor, this neighbor first. Okay, so this neighbor first, when we are visiting, we will check the distance, right? So right now it is having a distance of infinity. Okay, but what distance can it get? If we are coming from this particular node, right, it can get a distance of 0 plus 9, which is 9. Okay, 0 plus 9 is 9. Now distance 0 plus 9 is 9. 9 is less than infinity, right? So already it is having a distance of infinity. But if we come via 0, it will get a distance of 9. So we will change the distance and mark it as 9. Okay, this is the thing that we are going to do. Now what is the next thing that we will do? We have already visited one neighbor. Okay, so we will visit the next neighbor of 0. So which is the next neighbor? let's okay, you can consider 1 2 3 or whatever order the neighbors are given, or you will just iterate over all the neighbors. That's what you care about. Okay, so let's say we visit this particular neighbor next. So now what distance it's having? It's having infinity, but what distance can it get? It can get 0 plus 6, right? It can get distance of 6. So if it is getting a shorter distance, we will update it. So 0 plus 6 is 6, so I will update it here. Okay, and now we have visited this particular neighbor also. Next, we will try to visit this particular neighbor. Okay. So what we have done, we tried to visit the neighbors one by one. We visited this neighbor, made the distance as 6. Okay. Now we will visit the next neighbor of 0. Okay. So 0 had 3 neighbors. We have already visited 2 neighbors, which are 1 and 2. Now we are visiting the third neighbor, which is 3. Again, we will do the same thing, right? It is having a distance of infinity, but it can get a distance of 0 plus 1, right? It can get a shorter distance, so we will update it. So 0 plus 1 is 1. So what we'll do, we'll update this distance here. So when we are updating distance, what we are actually doing, we are updating distances here. Okay, so in the distance array we are actually updating the distance. So let me do that. So in the distance array, what will be update? For 1 we have the distance 9, for 2 we got the distance 6, for 3 we got the distance 1. Okay, so let me just update it. 9 6 and 1. Now we'll go to the next node. How do you select the next node? Okay, how do you select the next node? Now which node will give you shorter distance? This is a greedy algorithm, by the way. This is a greedy algorithm. So we are trying to find the shortest distance currently that we are seeing, and we are hoping that this shortest distance will give us a future shorter distance. Okay, so we will try to find the next node. Which node will you try to find? You have already visited 0, right? You have already visited 0. Okay, next which node will you visit? So next node we will select which is having the shorter distance. Okay, so I'll write it down. So which node will you select? Select the node every time which has shortest distance. Okay, because that is what is the greedy algorithm. We are always hoping that if we select the node which has the shortest distance, that will give us the best shortest distance. Okay, so this is what we are going to do. So we are going to select the distance which has the shortest node. Now let's select that. So among these, right, what are the distances that we can see? See, 0 is already visited. That is over. That is processed. What are the nodes that are remaining? So node 2 is remaining. It has distance of 6. Node 3 is remaining with distance of 1. Node 1 is also remaining with distance of 9. Among 6, 9 and 1, 1 is the shortest, right? So what we will do, we will visit this particular node. We will visit the node which has the shortest distance, which is 3 in this case. So we will visit this. Okay. So in visited, what we will do, we will change it and we can mark it to true, right? This is 3. So we will mark it to true. Okay. Now what we will do, we will visit the neighbors of 3. So we will visit the neighbors of 3. So 3 has how many neighbors? 3 has 3 neighbors. Okay, 3 again has 3 neighbors. But 0 is already visited. So we don't care of 0. Okay, 0 is already visited. It's already processed. So we don't want to visit it again. So what we will do? We will visit this neighbor, which is 1. Okay. Now we will again see if we can try to find the shortest distance. Okay. So what we will do? What is the distance that 1 currently is having? 1 is having a distance of 9, right? 1 is having a distance of 9. But what distance can we give it if we are coming via 3, right? How much distance will it get? It will get a distance of 1 plus 3, which is 4, right? It will get a better distance. So why will it settle for less, right? When it is able to get a better, shorter distance, we want to find the shortest distance. So we will update the shortest distance, okay? So distance that it can get is 1 plus 3, which is 4. So what we will do, we will update it. So now its distance will become 4, okay? So we have visited one neighbor of 3. One was already visited and now we have one more neighbor of 3 which is left. So which is the neighbor of 3 which is left? It is 2. Okay. Now we will try to check the distance of 2. Now see, 2 is having a distance of 6. But what distance can we give it? If we are coming via 3, we can give it a distance of 1 plus 2, which is what? Which is 3, right? So we will give a distance of 3 to it. Okay. So this has got changed. I'll change it back. Okay. This 1 plus 2 is equal to 3. So we can give it a distance of 3, right? So 1 plus 2 is 3. I'll make the change 3 here. Because 3 is less than 6, so I have updated the distance. Here also distance should be updated. Okay. So now after iterating over the neighbors of 3, what have we got? We have made the change in our distance array. So let me change it. In our distance array, what have we changed? Distance for 1 has got changed. Okay, from 9 it has got changed to 4. So I'll write it. From 9 it has got changed to 4 at this time. And what about 2? 2 also has got the distance change. Okay? So 3 was a very helpful neighbor. It helped us to make our distances even more shorter. So let me just go forward. Okay, so now let's go forward. Now what do we have to see? Now what do we have to check? We have to check for the node which has the smallest possible distance value, right? Smallest possible weight value, whatever you want to call it. So which are the nodes that are left to process? Only 2 nodes are waiting, right? They want to get processed. Among these 2 nodes, the distances are 3 and 4. So which will you pick? You will pick node 2, okay, because it is having less distance. So what we'll do, we'll pick node 2. Now node 2 has only 2 neighbors, right? Both of them are already visited, so it will not affect anything, right? So it will just remain as such, and we'll mark it as visited. Its neighbors are already visited. Now we will visit the last node. Now last node also has got all its neighbors already visited, right? All its neighbors are already visited. So it has 2 neighbors, both of which are already visited. So now what is our final answer? So let me clear it out so that we have our final answer. So this has an answer of 4. This is getting erased when I try to write. Okay. This has an answer of 4 finally. This has an answer of 1. Okay, let me write it again. This has an answer of 1. And what about this? This node has an answer of 3. Okay. So these are the minimum distances that you have obtained. Minimum distances from the source node, which is 0. So if you try to find the minimum distance, this will be your answer. And this is the Dijkstra's algorithm. Now there is one thing in Dijkstra's algorithm, and that is whenever you are trying to find the node, okay, that has minimum distance, right? You are trying to find the node that has minimum distance and you are picking it. Okay, so if you do a linear search to try to find the node which has the minimum distance, you will get a time complexity which is not optimal. So you can rather use a priority queue to find the node which has the minimum distance, right? And if you do that, you can improve your time complexity. So let us do one thing. Let us quickly run this algorithm again with priority queue. Okay, so that it will help us understand much more better. So I'll do one thing. Let me erase this and let us run this algorithm again. Okay, with priority queue. So if I erase this, okay, let me just erase this also. Okay, so we have our graph again. So let's now run it with priority queue. So let us quickly see that, and then we'll move forward to coding it. So this is our original graph, right? We have to find the minimum distances from the source node. Source node can be anything. Here let's just suppose for simplicity source node is 0, right? So depending on the source node we can find. So if source node was given 2, then you will have to run the algorithm starting from the node 2. Okay, now let's start. So how are we going to start? So initially we are going to initialize everything as infinity, right? So that is the first step. So the distances, that's a distance array that we are going to make, in which we are going to make everything as infinity except the source node, which is going to have value 0, right? All other nodes are going to have distances infinity. Now what we are going to do, we are going to have a visited array, right? Visited array, which will tell you if we have visited that node or not. So initially everything is false because we have not visited any of the nodes. Okay. Now apart from this, what we are doing, we are also having a priority queue, right? So I'll just write PQ for short, and now we'll see the algorithm with this priority queue, and then we'll move forward to coding it. Okay. So we have a priority queue. Now what we are going to do, we are going to push the distances in along with the nodes in the priority queue, right? Because we want, why are we using priority queue? We want to get the shortest distance node. That is what we want to pick at each step. This is the Dijkstra's algorithm, right? So in the priority queue, what will you push? We will make a pair, okay? And in the pair, what we will do? We will store 2 things. What are the 2 things that we will store? Let's say these are the 2 things that we are going to store. First, we will store the distance, right? Distance of the current node. Second, we will store the node or the vertex itself. Okay, so these are the 2 things that our priority queue will hold. So let's make a priority queue and we'll understand it better. So first, what we'll push in the priority queue, we'll push 0, and 0 is having a distance of 0, right? So that's what we are pushing in the priority queue. It is a minimum or the starting node, right? So now we'll start iterating over. So this node is visited, right? So what we'll do, we will also change it and mark it to true. Okay, we'll mark it to true. All other nodes are false, none of them is visited. The first node is visited, so we'll mark it to true. Okay, Now we will iterate over all the neighbors, right? We will iterate over all the neighbors of 0. So let's start. We will iterate over the first neighbor. 0 plus 9 is lesser than infinity, right? So we can change it here. So the distance 0 plus 9 is smaller than infinity, which is the current distance. So this distance will become 9. Okay. So this will become 9. Now we will change it, right? So this has changed and the distance has become 9 for the node 1. Okay, so this distance has become 9 and other distances are infinity. Next we will traverse the next neighbor, right? Okay, before traversing the next neighbor, we will push this in the priority queue. That is where we are using the priority queue, right? So we have changed the distance, so we will push it in the priority queue. So the distance is 9 and the node is 1. So we have pushed it in the priority queue. And first element, we will pop it. As soon as we pick it up, we will pop it. Okay. Now we'll go to the next neighbor of 0. Next neighbor of 0 is 3. Okay, let's just suppose it is 3. It depends on how you have stored the graph, right? So if the next neighbor is 3, then in that case, what will you do? 0 plus 1 is less than infinity, right? 0 plus 1 is the distance that we are getting, that is less than infinity, right? So in this case, what you will do? You will change the distance and what you will mark it to? You will mark it to 1. Okay, because if you are getting a distance which is lesser than the current distance, right? Why do you want to not take it, right? You want to update it for sure. So we will update it and make this equal to 1. Okay. So in the distance array also I will change it and make it equal to 1. Okay. So these are the current distances that we have, and we will also push this in the priority queue. So let me also push it in the priority queue. So now this is the use of priority queue, right? Your distance has become equal to 1, right? And the node value is 3. So what will happen in the priority queue? When you try to push 1 and 3, automatically the distance which is having less, okay, this distance is having less value will get pushed in the front. So what will happen? This element is not there in the priority queue. There are only 2 elements. So this will get pushed front. Okay, so this will get pushed front and 9 1 will go back. Okay, so this will happen in your priority queue. So the node which is having less distance will go front and the node which is having less more distance will go back. Okay, priority queue will order it itself. Okay, so let me write it properly. So these are the 2 nodes that are remaining in the priority queue, right? These are the 2 nodes that are remaining in the priority queue. Okay, they have got pushed. So now we will go to the next neighbor of 0. Next neighbor of 0 is 2, right? Now it is having a distance of infinity, but we can give it a distance of 0 plus 6. 0 plus 6 is less than infinity, right? So what we'll do, we'll change the distance. We'll change it to 6. So let me write it properly. We'll change the distance and we'll mark the distance as 6. And once we are doing that, we'll also push it in the priority queue. Now 6, the distance 6, okay, with the node value 2. Now this will go front in the priority queue, right? This will defeat 9 and it will go front in the priority queue. So let me do that. So 9 1 will come behind, right? So 6 2 will go front and 9 1 will come behind. Okay. So what is the priority queue that you will be left with? 1 3 6 2 and 9 1. Okay, 6 2 will defeat 9 1 and it will make its way itself before in the priority queue. So this is the current priority queue that we have. Okay, these are the 3 elements ordered by distances in the priority queue. So it's just a min heap, right? Priority queue is just a min heap. So it will get ordered. Now what we will do, we have visited all the neighbors, right? We have visited all the neighbors of 0 and we have made the corresponding distances, right? So this distance should also get changed to 6. So I'll quickly change it. So distance is 0, 9, 1 and 6. Okay. Now let us try to visit the next node. Which is the next node that we will visit? Whichever is having minimum distance. How we can see? From the priority queue we can see it, right? So we can just pop the first element in the priority queue. Which is it? It is the node which is having node value 3, right? So this will get started. Now we will visit its neighbors, right? What are the neighbors that it has? It has 2 neighbors, right? That are not visited. It has 2 neighbors, 1 and 2. So what we will do? We will visit both of its neighbors, right? So first, let's say we are visiting this particular neighbor, right? This particular neighbor is having distance 9. But what distance can we give it? 1 plus 3 is 4, right? 1 plus 3 is 4. 4 is less than 9. So we can give it a better distance. So we will change the distance of it and we will make the distance 4, right? So we'll make the distance 4. Okay, and while we are doing this, we'll also push it in the priority queue. So we'll push it again in the priority queue, right? So 4 and 1 will get pushed in the priority queue. Now 4 and 1, where will it get pushed? 4 is less than 6, right? So it will get pushed here. So let me write it here. Okay. So we have 4 and 1. So initially we had 3 elements. We have processed this element. Now 4 1 will come and get pushed in the front. So let me write it. So this is the priority queue 4 1, okay, 6 2 and 9 1. These are the elements in the priority queue that we currently have. I'll erase this. So now this is our current priority queue. Now what we have to do, we have to process the second neighbor of 3. Okay, 3 has 3 neighbors, out of which we have already processed the first neighbor. One neighbor is already visited and we will process this particular neighbor, right? So this particular neighbor is having a value of 6, but we can give it a value of 1 plus 2, which is 3, right? 1 plus 2 is 3, 3 is less than 6. So what we will do, we will erase this and we will make it 3. Okay. So 1 plus 2 is 3. So we have made the distance 3. Now we will also push it in the priority queue. So distance 3 and value 2. So where will it get pushed? In the priority queue, it will get pushed in the front. So let me write it here. It will get pushed in the front because it is having least distance. Distance 3 and node 2. Okay. Now we have processed all the neighbors of 3, right? We have processed all the neighbors of 3. Next, what is it that we want to do? We will also change the distance array. So let me quickly change the distance array. What are the current distances that we have? 0, 4, 3 and 1. These are the current distances that we have. And we will also change the visited array because we have processed the node 3 also, right? So we have processed the node 3. So we have processed node 0, we have processed node 3. So this is the current visited array. And now we have 4 more elements in the priority queue. So which is the first element in the priority queue? 3 2, right? So it will get popped. What does 3 2 correspond to? Node 2 with distance 3, right? It corresponds to this. So we will check it in the priority queue. So we'll pop it from the priority queue and we'll mark it as visited. Okay, now it has neighbors that have already been visited, right? Its neighbors are already visited, so we need not do anything. We have processed it. Okay, next, which is the next node that we have? We have the current node, which is having a distance of 4 and node value is 1, which is this particular node. Okay, so what we will do, we will quickly process it also. We will check its neighbors are all already visited, right? There is nothing left to process. So what will happen? Priority queue will become empty, right? After this, when we try to process the next elements, again everything is visited, right? So there is nothing more to process, right? Everything is already processed. And now a visited array also, everything will become true. Everything will become true in the visited array. So true, finally, after processing everything. Okay, so this is the final Dijkstra's algorithm that can be implemented. Now let's do one thing. Let's code it together so that it will be clearer after coding it. Okay, let's start. So there is a priority queue that we have to declare, and priority queue, we are taking pairs in priority queue, right? So let me take that. So pair in command, this is what we are taking in priority queue. And in priority queue, right, you have to give a vector. So this is how you have to initialize a priority queue. And now a priority queue by default is a max heap. Okay, by default priority queue is a max heap. If you want to convert it to a min heap, which is what we want here, right? Because we want to find the smallest distance, right? So you will have to give greater here. Okay? So you will have to do that. You will have to give greater pair inch comma inch. Okay? So let me just give that. So it should be fine now. So this is our priority queue and we have to give it a name. So I'll just call it PQ. Now first thing that we have to do is you have to declare a distance array. So let us declare a distance array, which is what we are going to finally return. So it will just have the same size as the number of nodes, right, which is v, which is given in this question. And initially you can mark all the distances at infinity. So in C++ you can mark it as int max. Now you can also check the source node, right? Now source node will obviously have the first distance as 0, right? distance from a node to itself is 0. So source node will have the distance 0. All others will be infinity. Now you can have a vector bool that is representing visited, right? So you can represent visited array, and in the visited array you can initially give the size of it to be the number of nodes, and you can mark it false. Anyway, by default also it's false. Just for clarity, I have given that it is false. Now we have to start looping over, right? So before looping over the priority queue, I have to just quickly push. So which is the first element that I have to push? I am pushing the distance, right? Distance is 0, and the source node, whichever it is, right? So I will push the source node along with its distance, and now I can start looping over. So while node of pq.empty, right? So till we are processing elements, we will keep running this loop. Now what is the first thing that you have to do here? You have to get the elements in the priority queue, right? So which is the topmost element? So pq dot top, what will it represent? So what are we pushing? We are pushing pairs, right? So if we get the first element, right, distance represents pq dot top dot first, right? And what is the second represents the vertex that we have pushed. For example, we push the source vertex first, so that is the vertex that we are pushing. Now we have got the distance and the vertex. What do you have to do? You have to loop over all neighbors of the current vertex that are not visited. Okay, you have to visit them. So that's what we'll do. Now how do you visit? So let's see what is given. So we are given a vector in adjacency list. Okay, so we will have to use that to loop over the neighbors. Okay, so that's what I will do. So let's see, vector int, okay, let me call it v, is equal to adjacency list of the current vertex, right? So the current vertex. Now we have got v. How is it represented? It is represented like this, right? So you have first the neighboring node, and then along with it you have the weight. Okay, weight is given to you. So this is given in the format of vector int. So you have lot of such okay, you have lot of such neighbors. So next neighbor is represented like this, and so on. So this is the format in which they have given us the adjacency list. Okay, so now what you have to do? You have to go to each neighboring node and then check if we can give it a better weight than it is currently having. So that's what I do. So for vector v, okay, for each vector v that is a part of my okay, for each, let me do one thing. I for each vector x that is a part of my adjacency list, right? So v represents something like this, right? This, suppose for the node 0, you have okay, you have 1 as the neighboring node. Okay, let's say this is 1 is the neighboring node, and let's say it is having a weight of 3. This is how it's given to you. So this is your v, this is your v. Let's say neighboring node is 2 with a weight of 4. So this is how it's represented. So what I'm doing, I'm going to each of the corresponding vectors. So I'm representing this as x. So I'm going to each of the corresponding vectors inside v, and I am trying to find out if I can give it a shorter distance. So now x of 0 is nothing but the node, right, that I have. So in node that I have is x of 0, and the weight of the current node, right, weight of the node is x of 1. Okay. Now what I have to do, if this current node is not visited, so if not visited of node, okay, so then I have to do something. So before doing this, okay, let me also say, before entering this for loop, what we have to do, we have to do two very important things which we have not done. First is we have to mark the current vertex as visited, right? And the next thing that we have to do is we have to pop it, otherwise this loop will run for infinite amount of time. So these are two very important things which we should do before entering this for loop. Okay, now what we have to do is if we have not visited the neighbor, right, then we can check if the weight that the current node is having plus the distance that the source node is giving it, if that is less than, okay, the current distance that it has, so distance of node, then you can happily do one thing, you can change its current distance. And what will it be? It will just become equal to this, weight node plus distance. and also you can push this element in the priority queue. So we will push it in the priority queue. And what are we pushing? We are pushing pairs in the priority queue. So what is the first thing that you will push in the priority queue? You are going to push the distance. So we will just push this in the priority queue. And what is the second thing that we are pushing? We are pushing the current node. So that's it. And now what you can do, you have completed your Dijkstra's algorithm, hopefully. This is the for loop that is running, this is the while loop that is running, and after all this you can return distance. Okay, so this is the Dijkstra's algorithm. Let me do one thing, let me run and see if it is working. It's working. Let me just submit and see if it's working. So it's working. That's it. Thank you for being patient and listening.